I just wanted to clarify that I made a small mistake, well, a big mistake last time. I think it was in stating the last property of unique factorization theorem. If you please, correct that. So the mistake was that I said that P1 is less or equal to P2 is less or equal to P3 is less or equal to PL. Here the inequality is strict, okay? This follows from this is the fundamental theorem of arithmetic. This follows from what we did. Okay, great. Now we'll start a new topic. Groups. Okay, so everybody, is it clear up there that the numbers? Yeah, okay. Okay. Let G be a set. A binary operation on G is a function let's call it circle, okay? This is not necessarily composition. I'll just call it circle for now, okay? A binary operation circle is a function from G cross G to G that sends a pair G1, G2 to its image that we denote G1 circle G2. Okay, that's a binary operation. That's a definition. It's a function from G cross G to G. Okay? This is how we'll define a binary operation. Let's give an example. Consider G equals Z. What's a binary operation on integers? What can you do with two integers? What you can do? Add them. Plus is a binary operation. Right? If A and B are integers, then A plus B is also an integer. Right? Are we good here? Great. That's a binary operation. What's another binary operation you can define on integers? What can you do with two integers? Yeah? Multiply them. Times. This is addition of integers. Let me see if I have a bigger chalk. Nope. Okay? You multiply two integers. If you multiply two integers, what do you get? An integer. Are we good here? Is it clear? Yes, sir. Just a bit bigger. Thanks. Yeah, I will do that. It's a binary operation. On Z, right? Multiplication. Okay, so if A and B are in Z, then A times B is in Z. So far so good. Are we good here? Yeah? Any question? This is a binary operation. Okay? All good? Great. Now we can define a group. For example, the real numbers. Can you define a binary operation on the real numbers? What's a binary operation on the real numbers? Yeah? Exponentiation. So you take x and y, you send it to x to the y. Well, for real numbers, you have to worry a bit of negative exponent, right? Of irrational exponent. Okay? Let's think about something easier. Yes? Say. Division. So on real numbers, can you always divide two real numbers? No. No. But what can you do with two real numbers? Add them. Multiply them. Right? Yeah? Great. Okay. Should I give another example? Yes, sir.
Is subtraction considered a binary operation, or is it just?
I mean, what's a function from g cross g to g? X, y to x minus y. Yeah. This is how I define it.
I was just wondering if it's considered distinct from like position to negative.
Well, I mean, it's a function, right? From g cross g to g. That's how we define it here. Okay? Great. Now, let's do other binary operation. Well, I mean, okay, that's definition. A group G is a non-empty subset, is a non-empty set, sorry, equipped with a binary operation let's call it circle, such that there exists an element, I'll call it E sub G in G, such that for all G in G, we have G circle EG okay? Again, circle doesn't refer to necessarily the composition of functions, okay? This is just a binary operation. I could have used star, but I prefer to use star later in the course for something else. Okay? Where do I have to write here? Okay? Are we good? 2. For all G and G, there exists an H. There exists H and G such that G circle H is equal to H circle G CG. Yes, sir.
So we say circle, it's not a composition, it's not anything?
It's a binary operation.
Yeah, but
Yeah. Okay?
I don't know how to ask my question, but we say it's a circle?
It's a binary operation, I just say circle. I called it circle. You could call it star. Right? Okay? I don't want to use like the other terms right now. But is it clear? That's just a statement. Okay? And 3. For all G1, G2, G3, G1 okay? I mean, these axioms or these definitions or these properties look a bit weird, right? Let's try. Let's try to check. Okay? That's a binary operation and a set G. Yes, sir. No, a group is with a binary operation. A set with a binary operation is a group if these 3 properties are satisfied. Okay? Example. Z plus is a group. Let's check that. Is it true or not? Is it true that Z plus is a group? Let's see. So technically here, what do you have? You have G is equal to Z, and the circle operation is the addition of integers, right? Circle is addition of integers in this case, and G is equal to Z. So let G be in Z. Well, I mean, that's not the best notation, but let's use it. Does there exist an element in Z such that G, wherever you have a circle, you replace it by plus? Can you find an element in Z such that G, this element E sub G, could you find an element in Z such that G plus this element is equal to this element plus G is equal to G for any G in Z?
Yeah.
Can you find that?
Yes.
What is it? Everybody? 0. Okay? Are we good? You know, in a annotation that is not very used, just write this. Okay? Yeah? Are we good? Is it clear? Everybody, is this part clear?
Yes.
I want an element such that when I apply the binary operation with any G with that element, and that element with any G, the same G as before, I get G. This element, this operation is addition. When I add 0 to any other element in Z, I still get the same element. Are we good here? Everybody? Any question? Okay, 2. Let G be in Z. I need to find an element in Z such that what's my EG here?
It's 0.
0. I need to find an element in Z such that G plus this element is equal to this element plus G is equal to 0. Can I do that?
Yes.
What can I pick for this element?
Minus G.
Minus G. Okay. Then minus G belongs to Z. And are we good here? Everybody, are we good? You had a question? No? Okay. Are we good? Any question here? Yes, sir. Yeah, I mean, let's try to stay away from that right now. Yes.
From the first one, do we have to like show or note that EG is unique, or could they be many?
I didn't mention anything. Just you can find an EG.
No, but then for the second one, you need to
Yeah. Well,
equal it to the
exactly.
EG.
Exactly. That's a very good point. I see what you mean. We'll show that this EG is unique. Now, in Z, can you find another element than 0 with this property?
No.
No. Okay? Can you find any other element such that when you add, for example, can you find an element such that x plus this element is equal to x if that element is non-zero?
No.
No. So if x plus something is equal to x, then that something must be 0. Okay? Yes?
What if Z was not like Z, like Z5
Yeah,
or something like that?
we'll
If
see.
it was,
We'll see.
it was just the modulus 5, for
We'll see.
example.
We'll see. We'll
That
see.
could exist, no?
We'll see. I mean, we're at the beginning yet, okay?
Oh, okay.
We're now at the beginning, so we'll continue. Yeah? Are we good so far? Now, hold on, that didn't get fixed yet. So, ooh. Can you see the third property here? Okay, look at the third property, please. Is it satisfied? 3. Let G1, G2, G3 be in Z. What can I say? Can I say that G1 plus G2 plus G3 is equal to G1 plus G2 plus G3?
Yeah.
Can I say that? This is associativity of addition. Okay, So Z is a group. Z with addition is a group. So far so good. I have a group, I have 3 axioms, I have a set and a binary operation. All I have to do is to check whether these 3 definitions hold, whether these 3 properties of a group hold. Z plus is a group. Okay, what is another what is another what is another operation, binary operation that I can do on G?
Multiplication.
Multiplication. Let's check. Can I erase here? Okay. Is Z with multiplication a group? Let's see, let's check the first property. Let G be in Z. Does there exist an element in Z such that G, what is circle here? Circle is times. Does there exist an element in Z
Yes.
such that G times this element is equal to this element times G is equal to G?
Yes.
What is this element? 1. Great. Awesome. Let's look at the second property. Please look at the second property. 2. Let G be in Z. Does there exist H in Z such that G times H is equal to H times Z? It's equal to what? What is my E here? 1. Does this exist?
No, not always.
Not always. Does it? When does it exist precisely?
When G equals 1.
Or
Minus.
minus 1, right? If G is equal to 0, does that H exist?
No.
If G is equal to 0, can you find an H like that?
No.
If G is equal to 2, can you find an H in Z like that?
No.
If G is equal to 3,
No.
4,
No.
okay? So, let's, if G is equal to 0, such H, sorry about that, does not exist. So is Z under multiplication a group?
No.
Okay, very good. Very good. So Z under multiplication is not a group. Are we clear here? Is it good? Actually. Yeah? This is like one of the most important concepts here. Okay? If you understood that, then it's very good. Okay? So what is a group? It's a set, non-empty set with a binary operation that satisfies 3 properties. Okay? Great. Now let's move on to more complicated stuff. Well, not much more complicated, but is R under addition a group? Let's see. Take R. Do you want me to write this down, or should I just say it verbally?
You can say verbally.
Everybody, should I write this down? Okay, so is R plus a group?
Yes.
Well, let's look at the first property. So let X be in R. Can I find an element in R such that X plus that element is equal to that element plus X is equal to X?
Yeah.
What is that element?
Zero.
Everybody. Yeah. X plus 0. My circle is plus X circle 0 is equal to 0 circle X is equal to X, right? And 0 is an R. Now, let X be in R. Can I find an element in R such that X plus that element is equal to that element plus X is equal to, what should be equal to? 0. Can I find that?
Yes. X
What is it?
Minus
Minus x. It's minus x. Minus x. If x in R, then minus x. Sorry about that. Then minus x is in R, and x plus minus x is equal to minus x plus x is equal to 0. 3. Let x1, x2, x3 in R. We know from the properties of addition, or from analysis 1, or whatever. It's not very obvious, actually. Okay? So R with addition is a group. Yes?
But since we proved that Z plus is a group and we know that Z is included in R, is it always allowed?
We can do an example. So for example, we can do an example. I mean, usually it's some other way around. You know that R plus is a group, and Z has some nice properties, then Z plus is a group. Okay? Good point. But I mean, you know, oh yeah, okay, anyways. Yeah, usually it's the other way. But I mean, you know, have you constructed real numbers in analysis? You take Z and then you construct Q and then you construct R? No? No, that's okay. Then let's not worry about that. Okay? Great. Are we good here? Great. Now let's try, is R under multiplication a group?
No, actually.
Is R under multiplication a group?
No, because the 0.
Let's think about it. Is R under multiplication a group?
It doesn't satisfy the property too.
Does it? Are we good here? So R under multiplication. Can I find an element in R so that when you multiply every element you get the same element?
No.
Can you find an element in R such that M
Yes.
times that element is equal to that element times M is equal to M for any M in R?
Yes.
What is this element?
1.
1, right? Now, can you find an element such that 0 times anything is equal to 1? No. So R times multiplication, R under multiplication is not a group. R under multiplication is not a group. Let me, okay, so let's do that. So let x be in R. Property 1 is satisfied. X times 1 is equal to 1 times x is equal to x. So let x be in R. Well, let x is equal to 12. Let y in R. 0 times y is equal to 0, which is different than 1. Okay? So if you have 0, you cannot find an element such that 0 times that element is equal to 1. All good here? Okay. Now, if y is different than if you pick any element different than 0, can you find an element y such that x times this element is equal to this element times x is equal to 1?
Yes.
Can you do that?
Yes.
What do you pick here?
1 over x.
1 over x. Very good. Okay, if x is different than 0, then 1 over x is in R. Okay, so R under, to make R with multiplication to a group, there is an element that I need to remove. What is that element? And everything will be fine afterwards, right? Let's do that.
No. But if you remove 0, then you can make the addition. Calculate the same.
Is R minus 0 under multiplication a group? I mean, first, I have to check something. That if you take the product of two non-zero real numbers,
You never get.
you get a non-zero real number, right? If A and B are different than 0, times b is different than 0. Right? So this times the binary operation on r minus 0. You take a product of two non-zero real number, you get back a non-zero real number. Agreed?
Yes.
Yeah?
Yeah.
Any questions on this? Great. Now, is it a group? Let x be in R. It's clear that x times 1 is equal to 1 times x is equal to x. Let x be in R minus 0. 2. Let x be in R minus 0. Basically, x is a real number, but it is non-zero. Does x, can you find an element is equal to 1?
Yeah.
What is that element? Everybody. 1 over x. I think it's good to participate. It's not bad. So let x1, x2, x3 in R minus 0. Then x1, you know this property, right? Okay, this is true. So R under multiplication is a group. What time is it? 11?
11.
Okay. Okay, we'll give other. Is it clear what a group is?
Yes.
I give you a binary operation on a set, and I give you a set, well, a set and a binary operation on it, and then you have to check whether these three properties hold. That's it. Okay, let's give an example. Well, let's give some property, well, some definition. 1, let G be a group. E.g. is called, now here I have to prove my claim, the identity for the binary operation circle. Okay? Identity means it does nothing. So you apply the binary operation, you get back the same number. M plus 0 is equal to what in Z? M plus 0 is equal to what? M. So adding 0 does nothing. Now if you take R, if you take this group, set of non-zero real number under multiplication, x times 1 gives you what? X, right? So putting this is called the identity for circle. Okay? 2. If G circle H and H circle G is equal to the identity, then H is D inverse. Again, D, I have to prove my claim. The inverse of G. Okay? And 3 is called associativity of circle. Okay? For now, I just want you to think of circle as a binary operation. That's it. Okay? Are we good here? Yes, sir.
So if we say it's a circle inverse instead of just inverse, or do we really?
Yeah, I mean, okay, under circle, say. Under. That's a good one. Under circle. Okay? That's a name. Okay? Yes?
What does the third point mean?
It's the associativity. This means that.
I mean, the thing is, it doesn't define anything new. In
No, I'm just
this
saying
one
what-
and second one, we're saying there's a name for those things.
Yeah, I mean, this is called
Three.
associativity. The property is called associativity.
But that's the name of the property.
Yeah.
That's not how you.
No, I
Don't
mean,
tell it to
this is how
me.
we define it. H is called the inverse, E is called the identity, and the third one is called the associative property. Okay? This is called associativity of rho.
No, I know this rule, but this is not naming anything.
No, I'm not naming anything here. But I don't think I use associativity here. Did I use associativity in this class? Did I ever use it? No, I don't think so. Yeah, so this is called associativity. Okay? I mean, you've seen associativity in linear algebra, right? If you multiply three matrices together, it doesn't matter in which order you start. In the sense that it doesn't matter which one you multiply first, right? Doesn't mean you can switch the order, but you can start multiplying them differently, right? Yeah? You saw this? Very good. Oh, I see what you mean. You mean like the definition here?
Yeah.
Okay, so that's okay. It's called. Let's keep it at this. It's not the end of the word. This is the name of the property. I mean, you're defining the property. Associativity is this, right? Anyways, great. Are we good here? Let's do something else now. Let's construct some groups. Do we like matrices or not? Yes.
In certain cases where they are easy to deal with.
Yeah. Matrices are very important, especially next course. So let n be an n. Let G, L, and R denote the set of invertible n by n matrices with real entries. Okay, now I consider GLN. Now GL means general linear. Okay, general linear group. Okay, is a group. 4 times is the multiplication of matrices. Okay? Great, let's prove that. First of all, if you take the product, I need to check whether, actually, if you take the product of two invertible matrices, is the product of two invertible matrices an invertible matrix or not?
Yes.
Why is that?
Because bijectivity.
Bijectivity of what?
No, it's because when you do the
No,
inverse of
bijectivity
the
is-
entire thing, it's the multiplication of the inverse on the other
Oh, okay.
oppositely. So
Yeah.
if you just define it that way, then you can make it into another matrix that obviously is the inverse of some matrix, meaning you can invert it.
Yeah?
But
Yeah. Very good.
I don't know how to say that properly.
So first, if A and B are invertible n by n matrices, very good. Then AB is an invertible n by n matrix.
No, it's not necessarily.
Okay? Under multiplication of matrices. Okay? AB is an invertible n by n matrix. Why is that? There are many proofs we can.
The determinant of AB is determinant of A times B.
That's another proof. Very good. So one proof is that AB is invertible. Multiply AB by B inverse. A inverse times AB. You get the identity matrix, right? Are we good here? Yeah? Or, another way to see that, the determinant, the n by n matrix is invertible with real entries. N by n matrix with real entries is invertible if and only if what? Its determinant is
Not zero.
non-zero. Now, the determinant of a product of two n by n matrices is the product of the determinants, no? Remember this? One way. Or another way, that AB is that A If both of these are non-zero real numbers, then that AB is non-zero. Okay? Those two reasons gives you that AB is invertible. Great. Yeah. So let A be in GLNR. So let A be an invertible n by n matrix. Can you find a matrix such that A times that matrix is equal to that matrix times A is equal to A? What is that matrix? Identity for any A in A. Great. 2. If A is in GLNR, can we find a matrix B in GLNR such that A times B is equal to B times A is equal to the identity?
Yeah, A inverse.
Yeah. If A, then A inverse belongs to GLNR, right? The inverse of an invertible matrix is invertible, right? And A inverse inverse is equal to A, right? Yeah?
Yes.
Or that A inverse is equal to 1 over that A. And that A is non-zero, so this is defined, right? Yeah? We good here? Yeah?
Maybe you're going a little too fast.
These are prereqs, okay?
That
This-
doesn't help.
This stuff you should have seen, okay? This is why I'm going a bit fast. Hey, what's up? What's up? Any question? Yes, sir. GL, I said it I think, but I didn't write it. It's general linear. Okay? Again, we should be very comfortable with linear algebra. Yeah, sorry about that, but it is what it is, you know. And you know that multiplication of matrix is associative, right? If you multiply A times BC, you can do BC first and then time it by A on the left, or A times B times C. Okay? You know this is true for matrices, no? Yeah? You know this or no? Yeah, definitely. You know this. Now try to prove it. Proving it is, I think next term you will see a nice way of proving this. Anyway, but yeah. Are we good here? Okay.
Next,
So,
next
yeah.
semester, as in what class?
Linear algebra. What's like algebra 2? It's linear algebra. You'll prove this. Okay? Yes, sir. Yeah. Why?
No, we didn't prove that.
You didn't prove the associativity?
Not in Math 236.
Oh, okay. Yeah, I mean you can prove it in a linear algebra by just writing down the big equalities, right? But then it's a bit long to write. In 1, 2, 3, I think you prove this, or you just define it. You just say this holds true.
This holds true.
Okay, so trust it, and this holds true. Okay? Yes.
Yes, I did.
I didn't say it's commutative. It's associative. Oh, and well, A with A inverse commute together. Not necessarily. If B is the identity, then yes, but it's not necessarily true. Okay, great. So are we good with what a group is now? Are we good with a group?
Yes.
Okay, now let's define another group. Today we're just defining some groups. And then tomorrow we'll define more groups. And then after tomorrow we'll discuss the properties of groups. Okay? Great. Let X be a set. And consider G to be the set of bijections from x to x. Then G is a group under the law of composition of functions. Okay. So take a set x and take all the bijections from x to x. The binary operation here is composition. Now first I have to check if I have two bijective functions. Is there from x to x, is there composition bijective?
Yes.
Yeah? That's your homework, right?
Yes.
If you have the composition of two bijective functions, the composition of two bijective functions is bijective. Are we good here?
Yes.
Yeah.
This is a lot of words.
This is, yeah, it is. But I'll write them down. Let f and g be in G. F, g from x to x are bijective. So G composed with f, here the circle is composition, from x to x is also bijective. Okay, now, do I have an identity element for this set?
Yeah.
For this set, is there a function where I could compose it with anything and get back my function?
F of x equals x.
F of x equal x, or the identity function, right? Let Ix, the identity on x, or 1x, denote the function from x to x that sends little x to little x. Okay? This is the identity function. Then, what is f composed with identity?
Just f.
What is f composed with the identity?
Just f.
Is f. Are we convinced or should I prove it? Should I prove it?
Go for
Should I prove it?
Yes.
The proof is not that difficult. So how do I show that two functions are equal? I pick an arbitrary point and I evaluate, and these two functions should give me the same answer, right? So let x be in x. F, the identity of x. What is that? This is f of ID of x at x. What is ID of x? X. This is just f of x. Now f and f composed with ID are equal at any point x in x. So f composed with ID of x is equal to f. Similarly, ID. Okay? Should I prove this again or it's okay?
Yeah, how do you show that one?
Yeah, so let x be an x. ID composed with f of x. This is ID of x at f of x. Now notice that f of x is an element of x, right? Because f is a bijection from x to x. Here f is in G, right? F being G. So this is just f of x. Okay? Great. Are we good here? Are we following? Great. Now, I need an inverse for f. Well, an inverse for f under the law of composition. Why does that exist?
Because
A
it's
bijective function has
an inverse.
an inverse. We've seen this, right? 2. Let f be G. Then f from x to x is bijective. Hence, what can I say about this inverse? It's also, what did we show in the homework? It's unique, right? Hence, that's why I call it f inverse. Hence, f inverse from x to x is a bijection, right? So f inverse belongs to B, and what? F composed with f inverse is equal to the ID of x, and f inverse composed with f is also ID of x. Here we have used the things we have learned previously, right? We have done these things previously. We have proved f inverse is unique. We have proved f inverse is bijective. 3. Let f from x to x, okay,
And with
be
this,
bijective. I mean, it doesn't matter if you're bijective or not.
you wrote the
Okay.
same thing, please.
Oops, yes, thank you. Right? This is true, right? We know that the composition of function is associative. So, if I have a set x, then the set of bijective functions on x, under the law of composition, is a group. Okay? What time is it? I have 3 minutes left, or 5? Oh, great. You can do one more example.
Actually 4.
Hence,
Yeah, it's 11:21, so.
okay.
Okay.
The
that's
set
okay. It's just.
of bijections of from x to x under the law of composition is a group. Okay? Now, if x is the set of integers from 1 up to n, we call Sn the group of bijective functions from x to x. Okay? So if you have a finite set, 1 up to n say, then the group of functions, the group of bijective functions from 1, 2 to n to itself is called Sn, S being symmetric group, called symmetric group. On n letters. Okay, now symmetric group of n letters is the set of all bijections from 1, 2 up to n to itself. Okay? That's it. So how many elements do you have in Sn? How many bijection do you have from this set to itself? Yeah? N? Factorial. Right? This was an assignment question as well. How many bijections do we have from 1 to, what time is it? I have, what?
2 minutes.
Sn
So we can choose n numbers for the first one, but the second
As
one we can only choose a minus
n
one.
factorial elements.
Let's choose one.
Okay, so basically you have n choices for f of 1. Now once you have chosen f of 1, you have n minus 1 choices for f of 2. If f 1 to n, 1 to n is bijective, then you have n choices for f of 1, n minus 1 choices for f of 2, and then 1 choice for f of n. So in total, Sn as n factorial Okay? So let's call it a day today. Very good. The thing is that you should really know what a group is and check the definitions. Okay? That's